Hey,
Hello, teacher.
hey, Daniel, how are you?
I'm good.
Good. Okay. How was your holiday?
Yes, I do. I play with fruit.
You did, huh? Okay. Did you guys have fun?
Yeah.
Good. Good, good, good. And you're back in school. How's school going? How was school for you?
Nothing.
It's what?
Nothing.
It's not. No, how is school? Is it good?
Yes, it's good.
All right. Anything else going on?
No.
Nothing else is happening for you? Okay. Are you doing anything this weekend? Going anywhere?
No.
No? Okay. Okay. All right. We're gonna work in literature anthology today. Yeah.
Okay.
And this is kind of where we kind of left off a couple weeks ago or 3 weeks ago, because we had reading writing last week or the week before. So now we're still talking about natural disasters. We were talking about earthquakes. Now we're going to take a look at tornado.
Oh, yes, tornado.
This is on page 60 for you, okay?
60. Yeah.
Yeah. Okay. So go ahead and read at the top where it says compare text.
Compare text. Read to find out what to do in the event of a tornado.
Tornado. Okay. Go ahead and read how tornadoes are formed.
When warm and cool air masses collide, the result can be a fast-moving, dangerous force of nature, a tornado. A tornado is a violent windstorm over land. Wind makes a rotating funnel-shaped cloud
Shape.
that stands.
A funnel-shaped cloud.
A funnel-shaped cloud that extends towards the ground. As it moves, it picks up debris.
Hold on. Debris.
Debris.
Yeah, the S is silent. You don't hear it.
Debris and objects in its path. Tornadoes are a natural process, especially in flat areas such as the middle of the United States. But tornadoes can also be unpredictable. They may cause destruction on one side of the street, yet leave the other side untouched. One way you can tell a tornado is coming is if you spot a funnel cloud. Other warning signs include sounds. An approaching tornado may sound like the rumble of a fast-moving train. It may also sound like a waterfall or like wind whipping into the open windows of a speeding car. Even after a tornado is passed, there are many hazards. Avoid standing on glass, sharp objects, or especially fallen power lines. Stay out of heavily damaged buildings that may collapse. It is important to treat a tornado as a serious crisis, as warnings may come quickly when little time to act.
Okay, what does it mean when something collapses? What is that?
Collapses.
What's collapse?
Stay out of heavy damaged buildings that may collapse.
Yeah, but what's another word for collapse?
Wow, this is a building, right?
So
You fall down.
fall down. There you go. Good. Okay, good job. Okay, so, and just so you can see, and I'll kind of show that little, I'll kind of draw this. This is a power line, right? This right here is a power line. That's how everything's connected to get our electricity through transformers. So many times in natural disasters like a tornado, these power lines can come, they can rip out and fall down to the ground, but they're still full of electricity. And so if you were to touch that, of course, you could die, or it would just electrocute you. So you stay away from these types of power lines and anything that is fallen to the ground, like big heavy buildings. You want to see? Hold on a second. I'm gonna share. I want you to see, because I think it's important to
This
see.
page has a tornado.
You want to see? Yeah, I'm going to show you like a real, like kind of images of a real tornado. Okay, hold on a second. I think it. You can see my screen, right?
Yeah.
Yeah. Images of tornadoes, just so you can really see even the clouds. Remember they're talking about a funnel cloud? This is what, and these are real pictures, okay? This is a funnel cloud. Do you see this?
Yeah.
Okay, this is what a tornado looks like. So
this is real?
This is real, okay? And remember they were talking about on flat, when you see the tornadoes on flat ground, that's how they usually will come. They usually, in the United States, we have them in the middle of our country on flat ground. And these are exactly what a funnel cloud looks like. Okay.
Oh.
So, and all that is strong wind picking up.
But teacher, look there.
Uh-huh.
There is a blue sky.
Yeah. There's it's only effective in certain parts of the sky. So when you see this whole cloud coming down, that cloud will finally touch the ground like this. See how it's coming down, and you see it touching that ground? Well, when that thing starts moving, okay, when this thing starts moving, it will start. Oh, here's a really good one. Look at this. And when that gets down, it's the wind, it's the cloud coming down. And so it's picking up so much. This is a really wicked one. This is bad. When big. Yeah. And when that comes down and hits the ground there with all those trees and houses and everything else, it destroys everything in its path because it's so strong. You can't fight it. I'm going to try to show you a picture of not just clouds, of maybe what it actually does. Okay, so these are real pictures. Okay, look at this one. This is a tornado coming down, right? It hits the ground, and you see all those pieces of things flying. That's all.
Is it real?
That's real. Yes, it's extremely dangerous. And they destroy that wind. That's just wind and maybe rain and whatever. But that's what it does when it comes through a town. It takes everything down, and it can kill a lot of people if you're in that path. Look at that wind. That's what it did to this house. And here's a really good example. See how this one side of the street, all the houses are destroyed, and look at this house here. Not too much. I mean, a little bit, right? And that's because that's where the wind, that's where the funnel cloud came down and went through. And so these are all real life photos. And as you can see, this funnel cloud, when it came down, it was coming, and the wind itself was just so strong that it was able to just take out any kind of place, any kind of building, houses, whatever. Power lines. Here's a good example. So see this power line right here, just so you can kind of see the example. This whole power line came down, right? And here's a power line, and you can't, the trees, everything. And these are all still powerful, live wires. So you can't get near those. You could be electrocuted if you try to touch that. Here's just really, really bad. But so I like when we talk about natural disasters or something with science or something like that, I like to show you real pictures so you get a kind of an idea what it really looks like, not just a drawing or something in a book, but these are real live photos and real live destruction, right? Cars, everything. I mean, just bridges. I mean, anything. Look at this car here. It's upside down. The wind turned that car upside down. Look at this car here. Look at them sideways. I mean, upside down. This one's on top of the other one. The houses, fell down. The tree branches, everything. But this is major destruction from.
Yeah, did you look this?
Yeah. There you go. Look at that. Totally destroyed. And then here's something interesting, okay? So here you have this whole house completely destroyed. However, look at the bushes. Look at
the bushes.
Nothing here, everything intact, right? So that's just the way in this part of the house, a little.
So we can see the tornado is like this.
Yeah, exactly.
Because this stairway house is
stand still. I mean, they got a lot of it. Yeah, but all this completely destroyed. Yeah, and here's another good example, just so you can see it, a tree root. And we're talking, a big tree. Look at this picture here. You see that root of the tree?
Yeah.
Totally out of the ground. Hold it up.
This tornado isn't big.
Yeah, I mean, look at. Here's another one. Whoops. Oh, this was taking a look at of a newsreel, but yeah, but I wanted to show you. No, they didn't do that one. Okay. All right. Anyway, we'll go back to the lesson. Okay. Anyway, so those are real pictures of tornadoes, and so that's what it looks like after damage. Okay, go ahead.
Tornado safety.
Read the sidebar up on top here first.
After a tornado hits, it is rated on a scale from 1 to 5. The scale rates the tornado on its wind speed and the damage it has done. When you hear or see a tornado warning on the internet, radio, or television, take shelter right away. If you are in a building with a basement, move to the basement quickly. Get underneath a sturdy, large object, such as a workbench or table. If you are in a building with no basement, move to the lowest floor. Find a center room away from windows. Crouch down to the floor. Cover your head with your hands. Avoid being in a car during a tornado. If a tornado is approaching, move inside a building if possible.
Okay. And once again, these are real pictures. So you see that funnel cloud going down. Okay, make connections. What should people do in the event?
What should people do in the event of a tornado?
Okay, what should they do?
When you hear avoid being in a car during a tornado.
Okay. What else? What if you're not in a car? What if you're in a building? What should you do?
If you are in a building, move to the basement. If the building didn't have basement, go to the lowest floor.
The lowest
Find
part,
a center room away from.
Okay. Okay. And then number 2, how are
tornadoes similar to other natural disasters?
okay?
Like earthquake, they all can destroy things.
Okay. Okay.
Wow.
There's a little an actual drawing. I like the illustrations. Okay, go ahead and read the question.
How can science help you find out how things work? Read how forces and motion affect our lives.
Okay. A crash?
A crash, crash in force and
forces and motion.
Forces and motion. About Max.
With Max.
Rolling. Maxwell J.
Axiom.
Axiom. Hometown, Seattle, Washington.
Seattle, Washington.
Hate.
6'1".
6'1". Weight. 192
pounds.
Eyes brown, hair none.
Okay. Is his super capabilities.
Super intelligence. Able to shrink to the size of an atom.
An atom.
Sunglasses give X-ray vision. Lab coat laws for travel through time and space. Origin, things birth. Max Asia seemed destined for greatness. His mother, a marine biologist, taught her son about the
a marine biologist. His mother, a marine biologist.
A marine biologist.
Hold on, Daniel. Biologist.
Biologist taught her son about the mysteries of the sea. His father, a nuclear physicist,
a nuclear physicist,
and a volunteer park ranger, schooled Max on the wonders of earth and sky. One day on a wilderness hike, a magchurch lightning bolt struck Max and blinding fire. When he awoke, Max discovered a newfound energy and set out to learn as much about science as possible. He traveled the globe, earning degrees in every aspect of the field. Upon his return, he was ready to share his knowledge and new identify with the world.
And identity.
With the world. He had become Max Young, super scientist.
Okay, so here we go. Forces that move us. And it's really important to read all the little side notes, okay? Okay. Start up here where it says super scientist.
Super scientist Max Axiom jumps right into the world of forces and motion at an amusement park. What a perfect day, even though everything feels turned upside down. Even though everything feels turned upside down.
Okay.
Spinning, flying, jumping, and falling are just some of the amazing ways to move. But there's a lot of science behind the zoom zoom around us. In fact, the world is full of all kinds of motion. Everything that moves needs a force to get it moves back for another jump.
To get it moving.
Oh, to get it moving. Back for another jump. Already? You bet. A force is any push or pull on an object. Bungee jump depends on a force called gravity. It pulls objects toward each other and it keeps us on the earth. Gravity is the reason I fall down, not up or sideways. Wheel moving can be thrilling, but I need a break.
What is she doing?
Snap, snap.
And what is she doing?
Hello, teacher.
Hello.
Okay. Hello.
Yeah. What is she doing? Yeah, you said snap, snap. But what is that a result from? What is she doing?
He's take a photo.
Yes. Okay.
Hi, Rosita. What are you doing here? Hello, Max. I'm taking notes for the physics class I teach. Why are you just sitting there? Is something wrong? Once I sit, sometimes it's hard to get moved again. But once I get going, I often can't stop.
Okay.
That's inertia for you. An object at rest. An object at rest tends to stay at rest. And emotion stays in motion. That's
an object in motion. Hold on, Daniel. Let's go back to that word where you read. You go, that's inertia for you. What? You might not know that the meaning of that word. Okay. But in science, but I know you haven't had these kind of classes yet, but in science, inertia is when something remains at rest. Okay. So like him sitting down on that bench he's resting, right? He's not moving. He's not in motion. That's inertia. Inertia is when an object is at rest. Okay. And when an object is moving, that is motion.
That's inertia for you. An object at rest tends to stay at rest. An object in motion stays in motion. That's Newton's first law of motion. Newton's first law of motion. A still object needs a force to get it moving.
Okay.
Likewise, a moving object needs a force to change its direction, slow it down, or make it stop. For instance, inertia keeps the stroller rolling. Wheel until another force comes along to stop it.
Okay. Now take a look at, because they talked about who Newton was, and it says that's Newton's first law of motion, and that's actually a person. Okay, that is a person that of course is no longer here, but his name was Isaac Newton. Okay, go ahead and read what he did.
Isaac Newton, in 43 to 1727 was the first person to release that certain laws of nature explain all motion on Earth and in space. He also was the first to explain the idea of gravity.
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 Okay. And so go ahead and where it says reread. Okay.
Reread. Why does a moving object need a force in order to change direction, slow down, or stop? Reread to check or understand.
Okay, understanding. Hey, Daniel, notice on a couple of words when you're pronouncing them, many times you're not using the gerund form, the ing, the continuous tense, like move. And this word will be moving.
Moving.
Make sure you read the entire word. But now and then also the word here just for pronunciation. Okay, you're right. In the pronunciation, it could be object, but only object if it's a verb. Okay, this is a noun. We're talking about an object. Okay, like this pencil. This is an object. Okay, this mouse. It's an object. Okay, it's a noun. This hook is a noun, an object. This is an object. Okay, so an object is a thing. Okay, any type of thing, right? Okay, yeah. So why does a moving object need a force to change direction, slow down, or stop? Why?
Be
clear that. What we talked about two things in this comic, right? What was Maxwell talking about? What were we talking about? Take a look at your book.
Object at rest tends to stay at rest, and object in motion stays in motion.
Okay, and what causes something? What causes something to be in motion?
Another force.
Okay, force. Okay, good job. Right, force causes something to be in motion. Okay. Continue.
To curb your
inertia.
You just need a little push.
Okay, and that's the force, right? Okay.
Yes. Come on, let's go ride the roller coaster. Let's move. Here we go. I feel like I'm being pushed to the back of my seat. That's inertia.
Okay, inertia.
When the ride starts, your body is at rest. When the chair moves forward, your body wants to stay at rest, but the chair moves into you. The chair's forward motion makes you feel like you are being pushed to the back of your seat.
Okay.
Wow, how does this roller coaster go so fast? The force of gravity is increasing our speed.
Good.
Speed is how fast we are going at any given moment. Acceleration is
hold on again. Acceleration.
Acceleration is how much speed we pick up as we go down the hill. Acceleration causes us to move more quickly at the bottom of the hill than we did at the top.
Okay.
That bar digging into my stomach. must be inertia too. You got it.
You got it. Okay. So what? Go ahead and read that last one.
The ride comes to a stop, but your body wants to keep moving. The lap
bar, which is this right here.
The lap bar applies a force
applies.
that keeps
Hold on, no.
applies a force that keeps you from flying out of the car.
Because that force of that bar is pushing down against you, right? To keep you, because with motion and movement, you want to go out this way, but that bar is forcing you to stay there. Okay?
So the lap bar stops us from continuing forward on the roller coaster. What keeps that stone from staying in motion? Excellent question. You can't see it, but a force called friction stops the stone.
Okay.
Friction happens when two surfaces rub against each other on Earth. Gravity and friction work together to slow things down and make them stop.
Okay, Daniel, give me an example of friction. So I know you understand that. What's friction?
Friction, like two hands is friction.
Okay. And what happens? Hold on a second. That's a really good example, Daniel. What happens when you put your hands together like that and you keep rubbing them together? What happens? What do you feel?
Hot. I feel hot.
Ah, very good. And that's the result of that friction when two objects are rubbing together. Okay, good job. Go ahead and read where it says here, friction in space.
Friction in space. In space, there is no friction. If you keep a stone, it would keep going and going. That's why astronauts are tied to the space station when they do space works.
They do space walks.
Otherwise, they just float away.
Okay, and then go ahead and read what it says here, where it says reread. How does
friction stop a roller coaster? Read page 70 to 71 to explain how friction works.
Okay, how do you think?
How friction works. Friction helps things to slow down.
Okay. But what on the roller coaster? The same thing in your car. If do you have a car, Daniel? Does your parents have a car?
We have a motorcycle.
You have a motorcycle. Okay. It's the same thing, it'll work. How does your father or your mother, if they drive the motorcycle, how does that motorcycle stop? What makes that motorcycle stop?
Like this is the wheel.
Uh-huh.
It has two things besides the wheel.
Okay.
When you want to stop, that two things will.
Do you have to do something? Do you have to do something on your hands? Do you have to?
Yeah.
Okay, so you squeeze, and that's this word right here, and you squeeze the brakes, right?
Brakes.
The brakes, and that when you squeeze that pad on the brake presses against the wheel, that causes friction, right? And you don't touch it, but if you were to touch it, don't ever do this. It would be warm, it'd be hot, but that's what's causing that friction causes that brake to stop.
Yeah.
Make the wheel stop. Yeah. Okay. Go ahead and the same thing on the roller coaster. Go ahead and read that.
Brakes on the roller coaster use friction to slow us down too. Come on, I will show you how.
Okay.
Each roller coaster car has two brake fins attached to its underside.
Underside.
As the cars approach the station, these fins slide between two sets of brake rails. I see when the brake rails squeeze against the fins, friction stops the cars.
Okay. So the same principle there, like on your motorcycle. When that's squeezed against the wheel, when that brake, it will make it stop. Yeah.
I had a great time, Rooster, but I've got to run. My nephew is having his birthday party over at
Skaters.
Skaters Paradise. See you later, Max.
Okay.
Juggling. These bowling balls is wearing me out.
Okay, and that's what this person is doing here, right? Juggling.
Yeah.
Okay.
I don't know why that guy is so tired. Juggling is easy. The juggler on the right is tired because he's using more force to throw and catch heavier objects. He show us Newton's second law. The amount of acceleration that
hold on, Daniel. Acceleration
that a force can produce depends on the mass of the object.
Okay, here's a question for you. What is acceleration? What is that? What do you think? What do you think that is? Give me another word for it.
Speed?
Yeah. Acceleration means to increase speed, right? To go faster. Okay. What's the opposite? What's the opposite of acceleration?
Slow?
Yes. To slow down then, right? Yeah, and then that's why you use the brakes to make you stop, right? So when you squeeze and you make the brakes touch the wheel, that stops, that slows everything down, stops. Acceleration's the opposite, that gives you speed, right? And that's usually like the gas pedal.
Right.
Good job. Okay, keep going.
What's mass, Uncle Max? Mass is the amount of matter in an object. The bowling ball.
Object.
The bowling ball has more matter in it than the tennis ball, so it feels heavier. Think about it. Which ball would be easier to juggle, Nick?
Okay, and I'll have you answer that question, Daniel. Which ball would be easier to juggle? The bowling ball?
The yellow ball.
Why?
It's easy to juggle.
Why?
Because the green big ball is heavier.
And why is that heavier? Why is the green ball heavier?
Because it's mass.
It has mass, meaning it's solid, right? It's thick all the way through. There's matter in the entire thing. It's not hollow. Give me an example of another kind of ball that is hollow, that's not solid mass. What other kind of ball do we have?
Ping pong.
Ah, okay. Okay.
Ping pong and a basketball.
Okay. Because how do you make that ball like a basketball or a football, a soccer ball? How do you make that thing bounce? It's not solid like a bowling ball. So how do we make that thing bounce? What do we do?
How do we make basketball bounce?
Yeah. What's
Like basketball, when you use very big force to hit it, you will feel that basketball is a little bit soft.
okay? What's in the center of that basketball or that soccer ball? What's inside of it?
Inside isn't
What-
it isn't have anything.
Okay, so what do we use? Because sometimes it can get flat, right? We can make it flat. Why?
Yeah. Oh, air.
Air. There you go. And air is light, right? That's like we have out in space. So that makes it light and that makes it bounce when we hit the floor or the ground.
Does the bowling ball can bounce?
No. Why?
Do you have
Why?
it?
Yeah, it's because it has too much mass. It's too solid, right?
It didn't have any air inside.
It doesn't have air inside of it. Yeah. I mean, I've seen occasions where you can get really, with a real strong force that could probably make it bounce a little bit, but not like a basketball or a ball that has air in it where it's light. Okay. You'll learn a lot more about this, Daniel, when you're taking science and physics and stuff like that. Yeah. But this is kind of just so you kind of have an idea of this. Okay. Gravitational pull. Go ahead and read that.
Weight is different from mass. Weight is determined by gravity's pull on an object. Each planet in our solar system has a different gravitational
pull.
pull. If you travel to each of the places below, your mass would always be the same, but your weight would be different. Multiply your weight by the number shown below each planet to find out how much you would weigh there.
How much you would weigh there?
If you weigh 100 pounds on Earth, you would weigh 38 pounds on Mars and 236 pounds on Jupiter.
So, and those are the mathematical formulas for each of those planets. And that's all based on different gravitational pulls. Okay, so if you were to take your weight and multiply it by whatever the number of the planet. Okay, go ahead, continue.
I have another way to think about Newton's second law. I need 2 volunteers. Pick me, I will do it. I'm going to push both of them with the same amounts of force on a level surface. Who do you think will accelerate faster? Jenny's bigger. He will go faster. No. Jenny's an awesome skater. She will win.
Okay.
Both of my arms are equally strong, so the amount of the force will be the same. Let's see who gets a faster start.
Who gets a faster start?
The girl.
Why?
Jenny.
Why?
Because the boy is bigger.
That's right.
He's heavy.
He's heavier, right? Okay, good job.
An ear will make.
She's lighter. She'll go.
Like the tennis ball, Jenny has less mass than Jen, so she gets a faster start with the same push. Joni will need a stronger force to get moving as quickly. I'm like the tennis ball. Does that make me a bowling ball? Uncle Max. Jenny wins the race on the flat surface, but I've noticed that the bigger kids always always travel farther than the smaller kids when skating down a ramp. Sometimes having more mass can give you an advantage. Let's have Johnny and Jenny race again. In the last race, we want to see who would get a fast start. This race is for this test. I'm going to release you at the same time. We will see who travels farther without pumping. Jenny's got it in the bag. No one. Jenny will beat him easily.
Okay. Now go read where it says make predictions.
Make prediction. Who will travel farther when released down the ramp? Use what you learn about forces and motion to make a prediction. Okay, so what do you think? Out of the two, who do you think is going to go further? Who's going to go farther? Johnny or Jenny? Jenny. And why do you say that? Because Johnny is heavier. Okay, but look how they are going down a ramp. Is that gravity or force going to have any advantage on someone who has more of a mass? Yeah. Huh? Take a look. Do you see that? Gravity pulls them down the ramp, but Johnny travels farther than Jenny. Ah. Why Max, is that? What happened? I got a good start, but Johnny just passed right by me. Johnny's larger mass takes more force to slow down or stop than your smaller mass. Do you understand that? Yeah. Okay, because Johnny is bigger, he has more mass. He's like that bowling ball. Okay, it's heavier, but if you start it from the top, and you have force pulling that heavy ball, it's gonna go longer. Like a paper and yeah, go ahead. Yeah, go ahead and read that. I'm going to have you do a little experiment though at home, okay? I mean, like if you're outside, take two for homework. Take two objects, maybe two balls, and make sure one of the balls are heavier than the other one. One's heavy, one's light. And okay, put them like on a hill or some kind of where like that, not a ramp, but like a hill, something that's high up, right? And release them at the same time. And tell me which one goes further. Okay, just drop them both on that hill and release them and see which ball goes further. Okay. Okay. If you have it, if you can do that. Okay, keep going. Time for cake. I don't know, friction between your wheels and the ground was the main force, slowing both of you down. Johnny needed more friction to stop, so he traveled farther.
Mhm.
Time for cake. I don't think these kids let a little friction stand between them and chocolate cake.
Okay, and this is about the author. It's Emily Son.
Emily's son lives in
Minneapolis, Minnesota.
Minneapolis,
Minnesota.
Minnesota.
Uh-huh.
She writes mostly about scientists and
Science.
science and health for kids and adults. Emily studied science in school. She even spent a few seasons following sea lions and seals to learn about them. When not writing and learning more about science, she loves rock climbing and running.
Triathlons.
Triathlon.
Uh-huh.
Steve
Irwin.
Irwin is a comic book artist. Early in his career, Steve contributed art to many superhero comics series, including Batman,
Batman Returns, and Superman.
the
Man of Steel.
The Man of Steel for his accomplishments in comics. He was inducted into the
Oklahoma Cartoonist Hall of Fame.
Oklahoma Cartoonists Hall of Fame.
Hall of Fame.
Others' purpose, a crash course in forces and motion were with Max exim super scientist is an information text written in the form of a graphic novel. This means that the information is presented graphically or in words and pictures that tell a story, much like a comic book. Why would the author choose to teach science concepts in graphic novel format?
Okay, so what do you think? Why did the author choose this way to teach about forces and motion and gravity? Why did the author use a comic book or comic strip? Why do you think?
Why would the author choose to teach science? Because he thinks science is important.
Okay, but why did the author use like a comic book? Why not just write about it in words without pictures like that? Why do you think the
make
author
us can see real things?
Do you like comics, Daniel?
Yes.
Okay, so maybe the author wrote it in a comic strip format to interest children like yourself, right? It's probably a little bit more interesting seeing pictures written like in a comic strip because most kids like comics. They like, reading about, different characters and superheroes and things like that. And so, and science sometimes can be kind of boring. And when you write it in a comic strip format like this, I think kids are more interested. Yeah?
Yeah.
I think so. Okay. All right. Daniel, I would like you to do this page for homework. Okay? Page
Okay.
79. I want you to answer the questions for homework.
Okay.
Okay. Make sure you write that down.
This
Page 79, answer the questions 1 through 4, okay?
1, 2, 3, 4.
1, 2, 3, 4. Mhm.
Okay. 4 is right about what a person's weight.
Uh-huh. You have
Okay.
now, and that'll be a math calculation because you have remember when we went over this page when we talked about the different planets? I know you have it written down right here on page 73. You're going to use these numbers to write about a person's weight if they were on those different planets. Okay. The formula how to do that is on this page. Okay.
Okay.
All right. So I think you can answer question 4 if you go back to page 73. Okay.
Okay.
And then we'll stop here on page 79 here. And remember, do this, and then next week we'll be in the reading and writing. Okay, we won't be in anthology. We'll be in reading and writing next week. Okay.
Okay.
All right. Daniel, any other questions? Anything going on this weekend?
No.
No?
Yeah. No.
You're not doing anything? No?
Yeah. Not anything.
Okay. All right. Is it your dinner time now? Is it time for dinner?
After 30 minutes.
Oh, in 30 more minutes you'll have dinner?
Yeah, I think.
Okay. Do you have another class now, Daniel, or no?
What?
Do you have another class after me?
No.
Oh, you don't. Okay. I didn't know if you had another class. Okay.
Oh.
Okay. Anything else? Any other questions? We still have a couple minutes if you want. I don't want to start another chapter though. Any other questions about this chapter, about any of the things that we talked about, like forces and motion and gravity and pull and anything at all? You understand the concepts?
Can you page 73?
Page 73?
Yeah.
Okay. Okay.
What's this? Means.
These are the factors. You remember you just read about that. Weight, they were talking about weight being different. Your weight, how much you weigh, that would be different depending on what planet you are on. Okay. So if you weighed, and their example was if you weighed 100 pounds, that's an easy number, 100, right? If you weighed 100 pounds on Earth, you would only weigh 38 pounds on Mars.
Oh.
Okay. And you would weigh 236 pounds because they're taking 100 pounds and they're multiplying it by 0.38.
Okay. Yeah.
And the same thing with Jupiter. If you took 100 and you multiplied 100 times 2.36, you would weigh 236 pounds on Jupiter. So
the sun.
But you would do it whatever. Now that's at 100 pounds. So let's say you weighed 50 pounds or 60 pounds or whatever it is. You would take that weight and multiply it by the factor of whatever planet you're going to be on. Okay.
Okay.
Now you understand it?
Yes.
Okay. All right. All right. So with that, then let's go ahead and clear that. All right. Well, then, Daniel, have a great weekend, and I will see you next week. Okay. Make sure you do your homework, though.
Okay.
All right. And next week we'll be in the reading and writing.
Reading and writing.
Yeah.
Okay.
Okay.
Workshop.
Okay. All right. Have a good weekend.
Okay.
All right. Bye, Daniel.
Bye bye.